I'm Justin Luczyk, Director of Optical Communications Programs at Space Micro. Today we're going to talk a little bit about optimization versus standardization. Now normally when we have these types of discussions, as it was last year, I'd like to have plenty of interaction throughout the presentation. However, this year with this format that's impossible. What I've tried to do is provide the material concisely and leave plenty of time at the end to have that discussion. Now, the picture you see on the screen is the vision from the SDA, and I think the essence of it is really applicable across a lot of different programs that are happening in the government. What the SDA is looking for is that fully interconnected backbone service, all done by lasers. We see that these key themes of interconnectedness, redundancy, and resilience kind of permeate throughout a lot of different LaserComm programs. This is a great vision, and what's displayed there is impressive, but it really is the technical vision. So what's important from the user perspective? They just want something that works. They don't care about the modulation or the wavelength. They just want the system to get their information from where it is to where it needs to go without even thinking about it. That's what's important to the user. So first we'll look at optimization, which is kind of the more traditional approach. Clearly, mission considerations drive the spacecraft and drive the link budgets that are available. But some of the key important parameters are what's available SWAP, the timeline of the launch, and the timeline really pushes what TRL level should be considered for your LaserComm terminal. Duration, cost is often an important driver, especially as we go to more LEO constellations that are looking for a low cost and a shorter mission life than a traditional 15-year GEO satellite. And of course, data rate is important as well as distance. Are these, LEO to LEO links at 5,000 to 7,000 kilometers, or are they GEO to GEO links at 80,000 kilometers? That really drives a lot of the design parameters, as well as atmospheric considerations. Are we space-to-space links only, or are we shooting back down to Earth through the atmosphere? The next piece of optimization is really looking at what standards are we going to go to. And CCSDS has published a lot of blue books and orange books, and SDA has come up with their own ICD, and these help drive the parameters that we're going to design the system to. The real challenge here is not all the standards published are in their final form, and many are evolving, especially as LaserComm is a newer effort. And these mission considerations and standards then kind of drive the design requirements. And this is where things get complicated. Pulled out of the SDA documents in particular, it says, while this open ICD defines many parameters for optical communications between the physical layer and link layers, neither the CCSDS standards nor this document is sufficient to ensure interoperability. And that is really the heart of the challenge, is with different vendors building these systems, even though there are a agreed upon set of standards, even if they're in draft form, that doesn't drive interoperability. And the other thing we keep hearing from customers is we want this to be a low-risk, non-developmental effort. That provides quite a challenge. So when it comes to designing the right LaserComm system for a customer, what are some of those key considerations? Wavelength. While most systems in the US are currently using 1550, there are actually a number of 1064 nanometer systems that are also used by the DoD. What kind of ranges are we looking for? Is this, 2,000 kilometer because it's LEO to ground, or are you looking 80,000 kilometer for a GEO to GEO link, or is it something in between? What waveform is being driven? On-off keying, non-return to zero, DPSK, QPSK, because that's really going to drive the next thing is what data rates are you looking for as a customer. We've seen everything from the very low end, a handful of megabits per second, to 200 gigabits per second and beyond. What's that mission need? And what's that mission life going to be? Is this, a CubeSat that might fly for a couple months? Or is it a GEO that needs to be on orbit for 15 years or more? And finally, this drives into the optics and the amplification. So that is a clear trade space. You can trade optical size for more power, but a lot of times the spacecraft is going to kind of drive one or the other. Are we going to be power limited on the spacecraft, and therefore we want to go with larger optics? Or do we really need to keep our volume of the system down, so we're going to opt for more power? And that's the trade space there. So what does the optimization really mean then in terms of configurations? So for this optimization design, based on the parameters described above, that gives us a total of 362,000 variations of systems, which is incredible. And that's really before considering any specific weight, look angles, or other design parameters. I mean, we've even seen systems that require transmit on one wavelength and receive on a different. So 350,000 plus is really just the starting point. Now, all this complexity is even further complicated by our customers' design goal of, yes, they want all these variations as non-developmental, low-risk items. So given the myriad of potential inputs, I think you can see that this is quite the challenge. And so how do we deal with this moving forward? At Space Micro, we've tried to take a more modular approach to the laser communications terminal. Really, if you look at the primary building blocks, it's an optical modem, an optical amplifier, a head, and the head also typically provides beam control and that pointing acquisition and tracking algorithm. This modular design approach with different component elements provides building blocks for us to customize systems more specifically to a particular user's need. That's important because having the maturity in each of the areas, be it the modem, the amp, the head, allows risk reduction, and it allows us to control the overall system with as few changes as possible. With a software-defined modem, we can host many different waveforms, typically either focused on OOK and DPSK for, I would say, more traditional needs, LEO to LEO crosslink type missions, but we can go up to much higher modulations in order to support high data rate backhauls as well. By using a variety of off-the-shelf optical amps, we can adjust the power level of the system to kind of tailor it to the need based on the optics that we're using in order to achieve the data rates required. And as you see up there, we've got a couple of different optical head designs, again, depending on the mission, what the field of view is, and things like that, which will kind of drive one optical head over another. Finally, our beam control and pointing acquisition and tracking algorithms are able to interface with the optical head and the overall system. We're really able to reuse that design regardless of the optical head size and just change some basic parameters in order to make it work for a given system. This approach really facilitates better management of the overall program and pushing risk down to lower component levels and not at the LCT level. Now, what you see here is that modularity that we talked about in practice and some of the designs that we've done and work that we've done in the past. You can see a couple different optical heads, configurations for crosslinks, optical amplifiers at 5 watts, modem systems, and really you can see how that modularity can be interconnected in order to tailor the LCT specifically to a customer's need. And while we're very comfortable with this approach at the company level, we believe that industry and government needs to come together and agree on some at least high-level standards. Really, standardization is going to drive interoperability, which we believe is key for adoption in the near term, as well as longer-term interoperability between different vendors, between different constellations, so that LaserComm can provide the robust backbone like the government wants it to. So if we look at the objectives, really lower cost, faster delivery, and interoperability, and how do we get there from here? Obviously, it's got to be joint between government and commercial, but we can never expect one terminal to meet all the mission needs. If, however, we're able to agree on the approach, then we believe that 80 to 90% of the mission needs can be met by a handful of terminals. Of course, there will always be one-off systems for very custom applications, but that shouldn't be the majority of what the focus is on. The focus is how do we get a handful of terminals to meet 80 to 90% of the mission needs. So what happens if we go through and we eliminate just a few of these variables? For example, standardizing on the 1550 wavelength, looking at range and saying, okay, we're going to do 5, 8, 40, and 80,000 kilometers. Being a 2,000 kilometer would be a LEO to ground type link, and that could also be accomplished by a 5,000 kilometer link. And then the 25,000 kilometers is kind of geo to ground. But if I could do 40, I can also do 25. If we work through the different parameters like that between wavelength, range, waveform, data rate, mission life, optics, and amplification, and just remove a handful of different variables, you'll see that the outcome is very different. This approach really gets us down to 3,600 different terminals, which is still a ton. However, this represents a 2 order of magnitude improvement. And we can also gain some further efficiencies based on orbits and use cases, being that, LEOs are probably never going to host massive systems, whereas GEOs are probably not going to need those shorter range systems. So that really allows industry and government to collaboratively work to optimize at the system level, understanding that there's a trade-off. A system may not provide the optimal performance given the mission needs, but if it can provide very good performance and it's much more available, it can be delivered more quickly at a lower cost. I think that kind of trade-off is what we need right now in this industry. In the long run, this is what's going to really allow adoption by more government programs at a much more rapid pace. And we feel that that's really important because as this industry grows, it needs to mature, and some level of standardization is part of that. So where does this leave us? Really, we believe that we can optimize based on standardized modules. By doing this, we allow heritage at the module level to fit the design needs for different programs. There cannot be a one-size-fits-all approach. Clearly, there's different missions and different needs. However, standardizing modules and standardizing the requirements around those types of modules will help the government and the program offices get what they need more quickly at a lower risk. Based on the number of recent RFIs and RFPs, it is very clear that demand for LaserComm and future systems is growing at a very quick pace. Laser is no longer seen as an exquisite technology and really has matured over the last number of years. Here at Space Micro, we have the flight heritage to deliver reliable laser communications terminals. And we've been working hard on this modular approach in order to build the terminals specific for customer needs. However, as a government and industry, we need to come together and really work on standardization across these fronts. We feel that this is critical to the next step in the evolution of on-orbit laser communications terminals. Exactly what I said I was going to do. I've tried to keep my presentation short to maximize the time for our dialogue after it. Obviously, there's a lot of different parameters talked about, a lot of different ways to standardize, be it frequency, be it modulation schemes, be it optic sizes. But I think it's important that we, at least at a high level, scratch the surface on where would it start making the most sense to standardize. When we went from 350,000 to 3,600 different variants, we didn't take out that many variables. And I don't expect us to be able to take out all the many variables at once. However, if we can even cut a few variables out of the overall equation, that will drastically reduce the number of systems out there being asked for. That'll allow us as an industry to more rapidly serve the government's needs to put those assets on orbit quicker. I appreciate your time today. And again, I'm Justin Luczyk at Space Micro.